The dilation on Heisenberg group that were defined by this formula have many interesting properties, among which being homomorphisms of the Lie group. We proved that property in the previous lecture, among other things, but we are yet to prove that the scalings work nicely with the sub-Riemannian distance. That lecture will come very soon, but I decided to give an answer to one of the questions that I put in the community, and many, I think 100% of respondents got it correct. The question was, if we fix a point and we define a curve simply by dilation, putting the r in the dilation, will this curve, will this continuous function be a horizontal curve? And the answer is that yes, if and only if the third component is 0. In which case the scaling coincides with the scaling in the R2 plane, and then we're looking at the horizontal, in this case literally horizontal lines in the xy plane that we had previously seen were horizontal curves. But when t naught is anything other than 0, we will never have this definition a horizontal curve. I want to show why both of these claims are true. A quick recall that a vector v at a point P, at a point actually xy t, belongs to the horizontal plane if and only if this holds. That is just by definition of horizontality of curves, or by definition of the horizontal plane, whichever you look at it. So this equality is the defining feature of v belonging to the horizontal plane at the point xyt. So we take derivative of our curve, which happens to be this, and then we need that gamma prime belong to the horizontal prime. So we take derivative of our curve, and we need that this vector belong to the horizontal plane at gamma r for almost every r. And if we apply the previous condition word for word, where these are playing the role of ABCs, we will need to have this equality. But then you get 0 for the right hand side, and if this is to be true not just for one r but almost every r, it forces t naught to be 0. The interesting part is that if t naught is 0, then this actually holds for all r values, therefore giving a horizontal curve. So that ends the proof, basically showing that gamma r is, or let's say just the curve gamma is horizontal only if, and also it suffices that if and only if t naught is 0.